the AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Yes, hello everyone. It's actually my pleasure to kick off this fall series of our AI for Good webinar series that is organized from the ALICE program, Machine Learning for Earth and Climate Sciences, specifically with the ALICE unit here in Jena. And we have a very nice lineup of speakers, and actually a very, very fitting speaker for the very first talk for kicking this off. So I'm really happy to welcome Hannah Kerner from Arizona State University, and she's such a perfect match because she actually has a background in computer science, then did her PhD in machine learning related to geoscientific questions. And she's also very interested in solving actual problems with AI. For example, she's the head of the artificial intelligence lab for the NASA Harvest program. So she's very much interested in food security and how we can predict these kind of things. But I'm sure she will also talk about this in her talk that I'm really looking forward to.
All right. Thank you, Marcus. I will share my screen now. Hopefully, this is visible for everybody. So I want you to imagine that there was a network of thousands of cameras arranged uniformly around the entire surface of the Earth with lots of different sensors attached to them. And imagine that these cameras are all set to capture images at the same time, every day, over 50 years. And all of these images that the cameras are taking are released to the world for free to use in any way that we choose. So this would be an incredible data set. This would be huge. What would we do with a data set of this scale, right? This would be like the Human Genome Project for the Earth kind of scale of data and detail of data about everything happening on our planet. What would we do with that? Turns out we actually already have this data. So we have thousands of satellites there. So these are cameras not on the ground, like in the opening example, but they're all just lifted up hundreds of kilometers or more into space. So we have this data set from satellites. Satellites have been observing the Earth and systematically recording images and other kinds of observations with many different types of sensors since 1972. And we have this record continuously till now and into the present, or into the future. And when I say that they're recording this data systematically, I mean that these observations for many of these instruments are happening at regular time intervals, regular spatial scales, regular spatial spectral resolutions. It's a very systematic and scientifically calibrated data set. So, for example, from the Sentinel-2 satellite, we have images everywhere on the Earth every 5 days with 10 meter per pixel spatial resolution. And from the Landsat satellite from NASA, we have images of everywhere on the Earth every 16 days at 30 meter per pixel resolution. From Planet Labs, a commercial satellite provider, we have images of the whole planet typically every single day at 3 meter per pixel resolution. And these are just 3 of the thousands of platforms that are observing the Earth right now. And the vast majority of this data are actually free for everyone to use for science, for society, for commercial purposes, for really anything we want. It's an incredible public resource. And so we have this incredible data at our fingertips. And some of you might be thinking, why is this not being used more? We should have all of the data we need to actually answer or address a lot of the challenges that we're facing on this planet. We have these thousands of satellites that are orbiting the Earth. Why are we not using this data more? Why is most of the satellite data that many people are familiar with is in Google Maps, which is just a tiny, tiny, tiny sliver of what is out there? These multimodal petascale satellite data sets have huge potential for giving us the information we need for tackling challenges at highly local scales, but also planetary scales, even on other planets sometimes, but that's not the topic of this particular webinar. So, these are providing information about agriculture, about the Arctic, about forests, about disasters, volcanoes, about urban areas, and populations. There's so much data here. And this is a critical resource for trying to meet the targets that are set out in the Sustainable Development Goals. In this paper here by Cavada et al., they go through almost all of the SDGs and show how studies are using satellite data to measure or meet the targets that are identified in each of those SDGs. So in particular, I have the privilege to work on SDG 2, the Zero Hunger, the most, with 2 organizations that are consortia operated by NASA or funded by NASA. And these are NASA Harvest and NASA Acres. So NASA Harvest is NASA's global agriculture and food security program under their Applied Sciences division and Earth Sciences. And NASA Harvest goal is to enable the adoption of satellite Earth observations by public and private organizations for the benefit of food security, agriculture, and environmental resiliency. And NASA Acres is a very similar program, but is focused on the US in particular, and has a lot of support for US specific challenges in agriculture. And so in my role as the AI lead for both the NASA Harvest and NASA Acres programs, I get the opportunity to learn from end users who are trying to meet the targets of SDG 2 and other challenges directly, and learn about what the biggest challenges they're facing and what kinds of information that they need but are not able to get from current resources. What information would help them make better decisions? So one example of this kind of decision making or information that organizations are looking for is a project that we have in collaboration between NASA Harvest and the Famine Early Warning Systems Network of USAID. So FuseNet aims to provide evidence-based analysis to help government decision makers and relief agencies plan for and respond to humanitarian crises. So with FuseNet, we have a project where each year they can ask us questions about something that they need some information about related to the impact of extreme events on agricultural cultivation. So they want to know how much has some extreme event, such as a disaster or a war, the COVID-19 pandemic several years ago, how has that impacted crop cultivation in a specific region? And they send us this request for analysis. And using our machine learning methods and remote sensing data, we can come up with answers to those questions or provide them information that's like this event X in region Y corresponded to some measurable change in crop cultivation in the year that they're interested in. And so, for example, last year, and now we're preparing another iteration of this for the second year of this question, is what the impact of the war in Sudan has been on crop cultivation and food security. So using AI and satellite data without ever having to physically go to a region to get information on this, which is typically the approach that organizations would use to try to get information about food security status. But you can't go there because of insecurity. And in many other cases, there are many reasons why we can't actually physically go to a place. And even if you can, these ground surveys can be very expensive. So using our AI and remote sensing methods, they're able to ask us this question in September 2023. And then just a couple of months later, we're able to give them this answer that cultivated area was significantly lower in 2023 in Sudan compared to 2022. And then they're able to use this information that we've extracted from the raw satellite data using AI to help forecast how these shocks will affect individual households and identify how they can support households that might need help in those circumstances and provide early response and early support to them. And in a kind of contrasting example, but in a similar theme, a couple of years ago, FuseNet needed to know what the impact of the civil war in Tigray was on crop cultivation during the civil war in northern Ethiopia. And again, very rapidly using these methods, or rapidly in terms of food security, so several months for the kind of policy decisions that we're trying to inform, we were able to show that actually the farmers in Tigray seemed like they were largely able to cultivate their crops at a scale that was comparable to before the war. So farmers were able to really weather this storm in Tigray, which was a very different situation than what was happening in Sudan, what we found this past year. So it's not always straightforward what you find in these kinds of analyses. And it's very challenging to extract this complicated, kind of complex stories from the satellite data using AI. And of course, we want those answers to be reliable and accurate and statistically robust so that we can be confident in our answers for very high stakes kind of decision making related to food security and zero hunger. So this work with NASA Harvest is, like I said, mainly focused on SDG 2, but there are many, many organizations who are working towards global scale impact across other SDGs as well, using satellite data and AI. So, for example, the Skylight project from Allen AI Institute is working on detecting illegal shipping vessels, or illegal fishing vessels, excuse me. And Global Plastic Watch is working on detecting plastic waste areas in satellite data. Global Forest Watch monitoring deforestation and forest land change. The World Cereal Project from European Space Agency is working to map cereal crop production like wheat, maize, etc., in the entire world on a regular basis, seasonally. Dynamic World Project from Google is trying to map the dynamic nature of land cover and land use change every 5 days on our planet. The SATLIS project from Allen AI Institute is trying to map renewable energy and other resources. Open Buildings from Google is trying to map has mapped all of the buildings in Africa. And Alan Coral Atlas at ASU is trying to monitor global coral reef health and characteristics to help inform reef management and restoration. So these are just 8 of many, many examples of people who are trying to develop AI algorithms for extracting information from these data. And this is such a hard challenge because, like I said, we have this huge amount of data. We have petabytes of remote sensing data that's been collected since 1972 and continues to be collected nearly every minute of every day. But that data is not the same as the information that people need to actually make more informed decisions from it. So there's a lot of work that needs to be done to turn that data into the actual pieces of information that people need for decision making about the SDGs and other aspects on our planet. So traditionally, the way we would try to do this with machine learning would be to use some supervised learning, or we would work with the decision makers, work with domain experts to say, okay, what is it you want to find? Let's identify many, many examples of what it is you want to find. Maybe if you want to map where all of the cropland is, we say, okay, you have to tell me what cropland looks like in thousands of examples in this area, in this region or time that you want to find it in. And then we would train our machine learning algorithm to look for that signal in all of the data to produce this predicted map of that phenomenon. But there's been a huge bottleneck in implementing solutions like that because although we have this enormous archive of data, very little of that data is kind of labeled and ready for supervised learning. So even if you label a fairly large data set in one country, that is still such a small part of the whole world. And that's only for one phenomenon or at one point in time. So there's so little of this data compared to what data are available that is labeled, and labeling is really time intensive and challenging to do for many things that we want to have these solutions for. So, historically people have said, oh, if only we had this labeled data set, if only we had the ImageNet of this domain or something like that, then we could realize the potential of AI for remote sensing data. But actually, the fact that we have so much unlabeled, systematically collected data in remote sensing is an enormous advantage in today's world of large language models or other types of foundation models that use self-supervised learning. So when I say that these data are enormous, I mean that these are data sets that are orders of magnitude larger than the largest data sets that we use in kind of mainstream machine learning. So, for example, the data set from Common Crawl from the internet that GPT-3 trained on was 45 terabytes before filtering. And that is essentially what a few of these satellites might collect in a single day. So there are over 66 petabytes of data only in one of these platforms' archives in the Copernicus data space ecosystem, which is from the European Space Agency. So the amount of data that we have for learning from, if only we could learn from this unlabeled data, is enormous. And today we've barely scratched the surface of what we can do with this amazing data source. So what I want to talk about today is not LLMs, but LEMs, or large Earth models, or as we'll see soon, maybe not so large models, maybe smaller, medium-sized models. But how can we leverage self-supervised learning to make sense of this huge, insanely multimodal and diverse data set that we have of unlabeled satellite data, and be able to extract representations that are useful in a huge diversity of downstream use cases, including agriculture, land cover monitoring, forest monitoring, methane plume detection. The list goes on and on and on and on for what we would like to be able to use these foundation models for Earth observation data for. So again, we have this huge data set and we have so much advancement in AI, and there actually have been several models in the last several years that have been proposed for geospatial foundation models. But we still don't see these models being widely used in practical applications. In all of those applications that I mentioned before, most of them are not even using deep learning. A lot of them are using like random forests and kind of what we would call more traditional machine learning algorithms. But this tells us that the methods that we have in artificial intelligence right now are just not ready for the data that we have in remote sensing. And so we need new methods to be able to really unlock the potential of that archive. So self-supervised learning and geospatial foundation models should be really useful, but there are some really significant challenges that are quite different than what we come across in natural images, or the kinds of images like digital photographs that we're used to working with in computer vision. So there, as I showed before, there are a huge diversity of tasks that we want these models to be able to generalize to. And so I've shown each of those tasks that I talked about before, each of those projects that I talked about before on the left-hand side of this table, in each row of the table. And there's a checkbox for each of the satellite sensors or platforms that are used in those projects. So for each of these, yes, they have some things in common, but there's a huge diversity of sensors and other kinds of products that these projects want to use as input. So a foundation model would need to be extremely multimodal, or be able to interpret many different sensors in order to be useful across all of these tasks. And in addition, they have very different ways that they want to represent data to the models for each of these applications. So for some tasks, temporal information is more important. Like in agriculture, we often want to have pixel time series that we're using, or in some other applications, how the signal changes through time might be more important than the spatial pattern of that signal. And for other applications, maybe the spatial structure is the most important thing, and time is not so important at all. Maybe for some other applications, having time and space and spectrum is necessary to be able to extract the signals that we want. So not only do these models need to be flexible to many different input sensors, they need to be flexible to many different shapes of inputs that we need to pass to the models. So if I'm a user of one of these models, if I'm one of these projects and I want to just load up a pre-trained model in my PyTorch ecosystem and be able to fine-tune that model for my use case, or use these representations from the model immediately, I need to be able to use whatever sensors or time steps are available and most appropriate for my downstream task. So if, I need to use synthetic aperture radar for Sentinel-1 or another platform, because that's what's best for detecting fishing vessels, for example, I can't use a model that's only able to ingest Sentinel-2. And so, I need to have some flexibility there. Also, we need these models to be performant everywhere in the world, not just biased to some regions where there might be more data. So, for example, this geographic bias is a huge challenge in existing products, geospatial data products that are derived using machine learning from remote sensing data. For example, in this cutout of agricultural areas in France in the top row and in Kenya in the bottom row, these are actually both showing nearly all cropland in the image. However, in the World Cover product, which actually I found to be one of the most accurate products that exists in Africa, it still misses nearly all of the cropland in this area in Kenya. And so you can see pink here is cropland. It's mostly accurately detected in France, but not in Kenya. And so, we need these products to be fair across all regions of the world and all kind of subgroups in the population that we want to represent. And in addition, remote sensing data, typically what we want to do is not just make a prediction about a single data point, but we want to make thousands or millions, maybe even billions of predictions about every sample covering an entire contiguous region or the entire world in order to form a map of our predictions. And this is quite different than traditional machine learning, where we train on a lot of data, but then at test time, we're making predictions usually about a very small number of examples at a time. So, detecting whose face is in one image. But in remote sensing, again, we need to make these dense predictions across an entire area. So this makes performance in terms of compute resources that are needed a really important consideration for organizations who are using these models. So, for example, for the World Serial Project from ESA, computational resources needed not just for training, but for inference, which, usually we measure computational resources needed in training, but inference time is really what's important for a lot of satellite data use cases. That was one of the foremost concerns for ESA World Serial. And for NASA Harvest, it's very similar. And so, as I said, there have been many promising solutions that have been proposed for geospatial self-supervised learning models in recent years. But there's still many limitations for kind of having the real world impact on these use cases that we want to realize. So most of these models have been trained on data from only one or maybe two satellite sensors. And if time is considered at all, it's usually maximum maybe 3 time steps, which is not enough for use cases like agriculture, where we want to see how things change throughout the year. Many of these data sets are also trained on quite biased data sets of the Earth, which often have kind of been carried over from the days of supervised learning, where we were relying on where we might have had labeled data. But these are generally a lot of the data sets that are readily available for machine learning are very biased towards North America or towards Europe. And many of them are very, very large. So this shows a 2-scale comparison of the size in terms of the number of parameters of several models that have come out in recent years, compared to the size of the model that we have currently deployed in the NASA Harvest pipelines for mapping cropland and things like that, like in the examples I showed in the beginning. So many of these models, particularly like vision transformer, VIT-based models that have 100 million, 300 million parameters, tend to be too large for efficiently fine-tuning, but also using it for large-scale, especially global inference. So what are we missing? A lot of this is happening, I think, because we're so used to working with a different type of data in machine learning. We're used to working in computer vision with 3-band color images, and these data sets that are really, really different than what we have in remote sensing data. And so the kinds of approaches that we've developed for these digital photography, natural image use cases, for things like, consumer products and whatnot, are really not aligned with the data that we have and the needs of the applications that we have in satellite remote sensing. So this is something that we talk about at length in a position paper that my co-authors and I wrote for the International Conference on Machine Learning this year, about how satellite data really should be seen as a different modality altogether, a different type of data than natural images. And we should really cultivate a whole subfield of machine learning research that focuses on that specific data and its unique characteristics and needs for applications of it. So how can we better leverage the unique character of satellite data in order to design models that are more practically useful for addressing our SDG targets and other needs? First of all, we know that there are many, many satellite data products available. We have many of these complementary sensors and derived products like land cover maps or other kinds of NDVI or vegetation health maps, all kinds of things that are all aligned in space. So we have these like overlapping views of the same place, often even at the same time, from many different sensors. And we collect this data everywhere on the planet. As I said in the beginning, this is systematically collected to have complete coverage. So we really have no excuse to have biased data sets in the self-supervised learning regime. And we also know that at the scale, the spatial resolution of most openly available remote sensing data, the data look very different than like a close-up image of somebody's face or things like this that we would see in natural images, where in those use cases, a very deep network that has a very large receptive field over the entire image might be needed. But with remote sensing data, several works have shown that typically shallower networks are just as good, if not better, than very deep networks. So we may not need the same kinds of architectures, and certainly not the same exact configuration of architectures that are useful for standard computer vision. And again, we have a really rich information in all of these different dimensions. So we want to be able to learn from the temporal dimension, spectral dimension, spatial dimension, ideally all at the same time. So recently, about a year ago, we released our model for self-supervised remote sensing called Presto, the pre-trained remote sensing transformer. And the driving design criteria for Presto was that it needed to be immediately useful in many different satellite machine learning use cases. So we at NASA Harvest want to use this model immediately, but we also wanted it to be immediately useful for many other types of use cases like those that we've talked about before. So we designed Presto to use a wide variety of input sensors for pre-training. So Presto is trained on Sentinel-2, optical multispectral data, Sentinel-1, synthetic aperture radar data, precipitation and temperature data from the ERA5 climate reanalysis dataset, the dynamic world, dynamic land cover dataset, elevation from a digital elevation model, as well as the location metadata and other metadata about these different channels. So all of these sensors are used for pre-training the model and can be used at test time. And when we train our model, our self-supervision task, and for those of you who may not be familiar with self-supervised learning, the idea is essentially that instead of having a label that is annotated by somebody about our data sample, we create kind of like a fake label for as a pretext task for training the model from the data itself. And one of these pretext tasks is masking parts of the image or parts of the observation. So you could think of it like if you're studying some text for a test, maybe you're like taking sentences out of your textbook and covering up the key terms and challenging yourself to guess what the missing term is or predict what the missing term is. So that's essentially what we're doing in masked image modeling or using mass autoencoders. So here, instead of kind of randomly masking out parts of the observation during pre-training, we design these structured masking strategies that mimic the kinds of missing data that our model would see in practice. So for example, masking out an entire sensor or an entire channel or an entire time step or group of time steps, these different strategies that allow the model, once it's been trained, to be robust to missing data in the input. So in this way, if a user only wants to use Sentinel-1 or only has Sentinel-1, they can just mask out all of the other channels and the model works just fine. So it's not phased by this missing data because it's been trained to be robust to that during pre-training. And we also in our architecture use only time series of at the pixel level across all of these different sensors. So this makes our model architecture much, much smaller than if we were passing in an image or a multispectral and multi-temporal image sequence. So by having this pixel level representation, it makes it very efficient. And it also makes it easy to use in many workflows that exist for agriculture and for some other use cases. So you can see here, this the size of Presto is not much larger than the model that was previously deployed in our NASA Harvest pipelines, and it's orders of magnitude smaller than other self-supervised models. And finally, we designed our pre-training data set to be globally representative as much as possible. So we sample data from each hemisphere, from each continent, from each biome, from each land cover. We really designed this strategy to try to create the most diverse and geographically and environmentally representative data set as we could. And that data set also spans multiple years. So we evaluated Presto across a wide variety of different downstream tasks. So once we've pre-trained Presto, we can fine-tune it and then test it on the much, much smaller supervised training sets of each of these use cases. So while Presto was pre-trained with about 22 million unlabeled data samples, for fine-tuning for each of these use cases, the data set will be much smaller. So we have use cases in agriculture with crop harvest and Sentinel-2 Agri 100, and forestry with TreeSat, land cover with Eurosat, wildfire, fuel moisture, and algae bloom detection. So these tasks all have a variable input shape or a number of channels and time steps and spatial dimension that are used. They have many different fine-tuning training set sizes. So some of these are very small as 200 samples, but some of them are quite large, as much as 45,000 samples. And lots of different types of tasks from a machine learning perspective. So some of these are classification tasks. Some of these are multi-label classification tasks, segmentation, regression, and they span a diversity of different geographies. So from Europe, South America, North America, Africa. And we find that from all of these tasks, Presto is able to perform competitively or on par with, or even better than, in several of these use cases, the models that previously were the state of the art, despite having 1,000 times fewer trainable parameters than many of those models. So it's much, much smaller, but because we've designed it specifically for the characteristics of satellite data, it's able to be more efficient with the parameters that we have. So what this means is that Presto is extremely lightweight and accessible to use. So to get started using Presto, it just takes a few lines of code and constructing a fine-tuning model. The whole model weights are only about 3 megabytes. And you can fine-tune the model on the fuel moisture task that I showed in the previous slide. Fine-tuning the model took only 6 minutes on a MacBook Pro. So it's very accessible for a lot of different users in the world, not just those who might have access to large compute clusters, while still performing as well as models that do require compute clusters. Presto, these are the different modalities in that table I showed before, the different sensors that Presto does include in the input. So it's still not all of the ones that are being used by these applications, but it's quite a good representation from them. And again, while I said that Presto is designed to ingest pixel time series only, because it's pixel time series, it can be adapted to work for images or multi-temporal images or image time series too, with very little adaptation. So the way we do that is we apply Presto to every pixel in an image. For example, in a 64 by 64 pixel image from the Eurosat benchmark task, and we extract the encoding or Presto features for each of those, and then compute aggregate statistics on those, and then pass that aggregated embedding to our downstream model. So Presto is able to be very flexible to different types of inputs, whereas an image-based model would not be able to work for the time series use cases that a lot of people, especially in agriculture, have. So you might be like, oh, seems like it would take a long time to process every pixel in an image. And it does take longer than processing it just at one time, but we are able to still do that encoding of the image much faster than existing models because the model itself is so much smaller. So for that Eurosat task where Presto is applied to images, while looking at every pixel, we can perform quite well, almost at the performance of other much larger models, while requiring 4 orders of magnitude fewer flops to encode those images. So again, we designed Presto to be useful not just to us at NASA Harvest, where we had some immediate use cases, but to other end users as well. And other organizations using it is kind of the biggest test of all for us. And so World Serial from European Space Agency, which I mentioned earlier, is trying to create these seasonally updated global cropland and crop type maps using machine learning and satellite data. They have now adopted Presto and are using that to map cropland and different crop types in phase 2 of their project, and have found that our Presto features that, again, were learned only from unlabeled data over the world in this self-supervised learning strategy, are able to outperform their expert curated features when each of those are passed to the same supervised classifier for a cat boost model. So it performs well both if you were to test on random data, as well as if you were to split your data spatially so that the model is only fine-tuned on certain countries and then tested on certain other countries that were not part of the data set. And also when you split that data by years, so if you train only on one range of years and then test on years that have never been seen by the model before. So these Presto features were not just more accurate, but much more robust to different distribution shifts at test time compared to the expert features. And we are also using Presto in some really challenging use cases. So for example, we have a project in Maui in Hawaii where we're trying to develop agricultural data sets that will support indigenous farmers in Maui County and help increase food security on the islands in order to help serve the community's needs there. And so we've been able to create crop type maps of relatively rare crops like taro, which is an important crop in the Hawaiian diet, with a very small number of training points. So in this example, we had like 20 ground truth examples of taro, so about 20 labels, and could still train the model to produce a fairly accurate map of where taro might be growing. And then we can use those kinds of maps to monitor crop conditions in crop specific or cropland growing parts of the islands, and be able to give kind of crop specific insights to farmers and other community members from the satellite data in those regions. So we've recently launched this newsletter project called the Maui Nui Crop Monitor, which is providing these monthly insights about agriculture on the islands in Maui County, which has really only been enabled by having these kinds of cropland and crop type data sets that we could create with these machine learning models that are very label efficient. So we want to have impact with the models that we're creating from machine learning and remote sensing. Of course, we want impact factor too as academics. We want our work to be cited, but we really want to have impact on these real world challenges. And that often requires doing things or approaching problems differently in some ways than we might if we were just after purely academic rewards. So I want to share a few thoughts on how I think we can do research that is more impactful in machine learning for remote sensing, not just kind of attractive from a research perspective. So we really need to consider the specific context that we're working in. It's often our practice in machine learning to kind of treat the end user, quote unquote, as like a black box, this like hypothetical people in the future, or, we're just kind of working on the algorithms from an algorithm perspective and maybe looking for use cases that it might be useful for, but our lab experiments are really separate from the reality of those use cases. And so I think that we really need to consider the context of how our models are going to eventually be deployed and how they would be used to make sure that our designs and our lab experiments, our research experiments are actually representative of those kinds of scenarios and are resulting in fair, safe, and robust models. Again, as I said, we often treat the end user as kind of this like hypothetical later person who will use our models. But I think it's important to not just think of those as people we might go to at the end and say, hey, would you actually use this? Or what do you think of this? But to include them in our projects in the beginning as really co-developers, not just like outside perspectives, but they have really important requirements and insights and expertise that can help to advance not just the applications, but the foundations of our machine learning research. And this is something that we talked a lot about in another position paper at International Conference on Machine Learning this year called Application-Driven Innovation in Machine Learning. And we also, in my opinion, should not think of deployment, again, as some future step that somebody else may do, but deployment or testing how something actually works in the real scenario that we're saying it should work for should really be considered part of evaluation, in my opinion. So this is often really hard as academics to do because our work usually concludes after we report our metrics in a paper, we beat the state of the art, and we're like, yay, we're done. And it takes a huge amount of time and often cost in order to actually work with people or deploy it ourselves in some realistic scenario. But that work is not just rewarding from an impact perspective, but it helps to reveal limitations in our research and in our machine learning methods and practices that inspire new research questions that we can try to solve to make these models more usable. And I love this quote from Kiri Wagstaff in her paper in 2012, Machine Learning That Matters, that to the rest of the world, these real-world deployments of machine learning are the only visible advances of machine learning to the rest of the world, the only way that we contribute to the larger realm of science and human endeavors. So if our work is stopping in our academic publications, it's really not mattering to the rest of the world. So we also need to have these diverse teams and funding sources to make this kind of work possible. So I am not an expert in agriculture. So in order to have impact in agricultural use cases, I work very closely with agricultural experts like Catherine Akalembe and Inbal Becker-Eshef here, and on user-centered design and knowledge systems like Anna Tarano here, and amazing PhD students and researchers who come up with a lot of these ideas and implement all of these systems and experiments like Gabriel Tsang and Ivan Zvonkov and Gideon Mohawanayo here, and collaborators on machine learning methodologies that we can really push the envelope forward on the foundations as well, like David Rolnick. So these are all collaborators on the work that I presented in this presentation, and some diverse funding sources that we've had to make this work possible. So I want to leave you with this summary that some points that we can keep in mind in order to provide information and support decision-making in the real world using geospatial foundation models, that they should be generalizing to a wide variety of tasks downstream. They should be flexible to diverse types of inputs and shapes of data that need to come into the model. They need to be efficient, globally representative and performant, easy to actually get started with, to evaluate and then use and deploy, be co-developed with the end users who would eventually use them, and be co-developed from the beginning, not just kind of at the end of the project. And most importantly, they should be able to be used now, not in some hypothetical future, because we have these really urgent challenges like the SDGs that we need to address on our planet before it's too late for us to do so. So again, there's so much potential in this this satellite data archive that we have to tackle these different challenges at many different scales and in many different domains. And machine learning really is the key to unlocking this data source and extracting information that we need for addressing challenges on our planet. But we need to really push a new type of machine learning methods and really novel methods that are designed for that data and the use cases we need to solve in order to have that impact. Thank you.
Thanks a lot, Hannah, for this really fascinating talk, covering really a lot of ground, both technical and also more big picture. So this was really very enjoyable. Thanks again. We do have some questions. I would also have some. Let's see, but we have 2 questions currently from the community, from the chat. I can read it out. You probably can also read it yourself, but for everyone, I will read it out. So Nushin Adian is asking about the evaluation of the small models. So are the accuracy and efficiency of small models validated for high multi-classification cases? So maybe you want to comment on that.
Okay. Yeah, thanks for the question. I think I'm assuming what you mean by high multi-classification use cases is where we might have either multiple classes that we want to predict, or maybe even a very large number of classes, like in, let's say, like species prediction or something, or where we might have multiple labels that would be assigned to a single sample. So it might be like both forest and cropland in an image. So the tasks that I showed do include some multi-label classification use cases where there's multiple labels that would be predicted for the same sample. We don't have any use cases that are like a really high number of classes to predict. That would be a really interesting one to use. Typically the way, if we did that right now, like we would represent it as like a one versus rest kind of thing, where we would use one of those classes to predict like a dominant class and predict everything else as maybe an aggregate class. But I don't actually know of any data sets that have a really large number of classes or like a long tail distribution for remote sensing data. But if somebody knows of them, please share.
Yes. The next question is about the masking strategy. So how do you do the masking? Do you replace mask paths by random values or hide them? So declare them as missing.
Yeah, great question. So historically, like before transformers, we would do this task called in-painting, which would be basically zeroing out blocks of the image. So in like convolutional neural network days, where we were just analyzing the pixel values directly, we would replace the pixels by like a 0 value or some constant like that. But what we do with transformers for masked modeling is we basically turn the token for the masked tokens into an explicit mask token. So there's like a special token, a mask token that is passed to the model instead of the embedding for that token. So if this was an image, for example, and we have patch tokens like in a vision transformer where each like 8x8 or 16x16 pixel patch of the image is turned into an individual token, and then those get passed to the model. For the masked ones, we would just replace that with a mask token.
For me, sorry, for me, just the internet went away, but I I think you finished with that answer, and I totally agree. Actually, I have a question myself also regarding this. You mentioned basically that with Presto, you can also do tasks that actually ask for a spatial context, like the segmentation, for example. And I think you mentioned basically that you do a post-processing of the features in Presto, but it wasn't totally clear. So basically, you said you do some statistics also, but you could also basically do some lightweight convolutional neural networks or so to basically get the spatial context, or I would be interested in that.
Yeah, you're right. So you could, right? So the way we do it is just like not modifying the architecture, but modifying how it's used downstream in order to process each pixel individually, or that would be like in the case of segmentation, you could just make the prediction for each pixel. But in the case of an image level classification or prediction, we would take like all of the embeddings and get the mean and standard deviation of the embeddings, and that is the representation that's used in the downstream model. But you're right, we could have some sort of convolution or some way of also natively analyzing the actual spatial structure of the images too. The challenge in this version of the model is that we didn't want to like make the architecture more complicated or make it kind of like unusable for the pixel time series use cases too. So it would have to be flexible to any shape of input. However, stay tuned for our future version that we're working on now that is designed to handle flexible input shapes and analyze them directly. So we will be handling those different shapes in the model input processing, not just in the downstream use of the embeddings.
Okay. Don't see other questions. Maybe then I have one other. So maybe a more general question. I found very interesting that you correctly talked a lot about data, and you talked also about the masking strategies in some detail. So, and not so much about the architecture. And I think that's also a common theme that actually, if one thinks about good performance regarding also the downstream task that one has in mind, while it should be still general, probably the masking strategies are pretty decisive, right? So what is, I mean, what is a good way?
Yeah.
I mean, at the end, the masking strategies replace a hand design of features to some extent.
Mm-hmm.
So I don't know what you thought on that.
That's true. Like, how sensitive is it to, like, if we had done random masking instead of these structured masking strategies, for example.
Yeah.
So, and for us too, like the masking strategies were a way to be robust to missing data at test time. So it was really like a design feature as well as a useful pretext task. But in some cases, people have shown that there's not a huge difference between masking strategies. But for us, we have an ablation study in our paper that shows that using all of these structured masking strategies is significantly better than just doing random masking. But I think your question gets to like a bigger trend and concept in machine learning research now that, you know, people used to be so obsessed with architecture design and like, oh, this is my like conv transformer, whatever, like these crazy architectures that I think now we're finding really don't make a difference. And really what drives robustness in models or differences in performance between them, these actually improvements that matter at test time, is the diversity of data and those kinds of tasks that the model is learning on. So there's been some work, for example, with CLIP models, contrastive language image pre-training, which really like changed the game in terms of model robustness to out of distribution data. that it was not the model size or the data size or the architecture, any of these kind of usual suspects for what people think matters in machine learning, but it was the diversity of the pre-training data that was the most important. So I think that's a major trend in machine learning now.
Thanks a lot. Yeah. So there's another question from Jakob Bruin, commending you for your interesting presentation, and he's asking if you have considered co-training your model with a small language model that can answer questions and give advice about the data and implementation of the model.
We have not, but I think that's a cool idea and could help serve a lot more end users because, you know, it's still not like something like ChatGPT where it's like ask question and get the answer. You still have to prepare your input data from the satellites and, you know, you have to be able to frame the question that you want. This kind of prompting for these models is really, really early, like prehistoric days in machine learning for remote sensing right now. But I hope we'll see more of that in the future.
Thanks. Actually, maybe one more question that was kind of triggered, or now you would say prompted, by one of your first slides, and where you basically had events and then the effects of events. So I think it was. Yeah, I think you had several examples, so kind of even war and these kind of things. And I was wondering at that time, point, but also later, what do we do actually about causality in this context? So because I mean,
Yeah.
what the causality of these kind of associations is maybe not always clear, and let's say a normal representation learning model probably can also not, without any other ado, address that, right? So I don't know if you have any thoughts on that.
Yeah, that's a great question. We've exactly, that's come up in this work so many times because if we show a change in cultivated area between like a year where the war is ongoing and a year where it's not, and there's a reduction, that doesn't prove that the reduction is because of the war, versus some other confounding factor, maybe it was just really dry that year or something else was going on, right? Or if there's an increase, is that due to precipitation or did, you know, people actually move to a place and grow more food? So causality is a really important question that end users are really interested in having answers to. But like you said, it's super hard to do right now and really not like accommodated by our existing approaches. I think that's starting to change. A lot more people are starting to work on that. But right now, the way we address this is to try to rule out some of these other factors, like showing that variation cannot be explained by precipitation or these other factors that would be driving changes in a non-conflict year. So, you know, what are the different things that could be responsible for variation? And we also, in the specific case of conflict, there's an amazing data set from a project called ACLED, which has the locations and times of reported conflict events, like different battles or different activities that take place. And so we can look at you know, for example, what the change is in the immediate neighborhood of these events versus outside of them to help also see the change, explain what might be driving the change.
Thanks. So we have one more question. I think then we should close this webinar. Question from Moyen Ranson. Again, also commending you for amazing presentation. He's saying you have used mask autoencoders for pre-training. The new path that image foundation models have taken is based on the presence of objects in the image. This Dino family of models. And as you mentioned, remote sensing data is a different modality. Do you think this new trend can be still applied on remote sensing data?
Yeah, so I think what this question is getting at is that masked modeling is only one of many different types of pretext tasks that we could use for pre-training models. So we could also do contrastive learning where we're saying, okay, like this image from Sentinel-2 and this image of the same place from Sentinel-1 are similar. So find representations that those have a small distance in versus like this image in Sentinel-2 and this image in Sentinel-1 from different places should be far apart. Or there's a paper called Seasonal Contrast that does this for saying, you know, okay, all these images were taken of the same place in different seasons, so they should have similar representations compared to images of other places in different seasons or locations. Or there's also like autoregressive pre-training where we could say like predicting the next token iteratively. This is often used for language modeling, like GPT predicting the next token and the next token and the next token. And so there are some other strategies too, but these actually have, can't think of any work in autoregressive token prediction for remote sensing, but certainly like contrastive learning and other mass image modeling and other types of pretext tasks have been proposed for remote sensing data and machine learning. And it is a different modality. And I think that there's a lot of new types of pretext tasks that we can explore, or framings of these existing pretext tasks based on the structure of that data. One example of that is our structured masking strategies, which are specifically designed for that modality. And, you know, the seasonal contrast example for contrastive learning also designed for this like repeat coverage of the same places that we have in remote sensing. So I think there's a lot of opportunity for expanding on these kinds of methods that have been developed in computer vision or language modeling, but kind of redesigning them for remote sensing data.
Great last words for this. So let me thank you again, really, for this very, very nice and amazing talk. Everyone else also for the questions, and stay tuned for the webinar. The next one is in two weeks, I think. And feel free to contact Hannah for sure, I guess, also myself if you're interested in stuff. And also one can connect in the neural network. Actually, after the talk, I personally will not be available. I don't know, Hannah, if you would be available to go into this.
I have to run, unfortunately.
You have to also run, yeah. So, but maybe there's discussions within the community so that everyone could take advantage of that. Great. So thanks again.
Thank you, Marcus. Thank you, everyone.
Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Mm-hmm.